All right, now that we have set the stage for the KSP, I want to spend some time talking about the precipitation reactions. In chapter 4 in GenChem 1, we learned that a precipitation reaction can occur when you mix two solutions containing ionic compounds when one of the possible cross products, which is a combination of the cation of one and the anion of the other, essentially is an insoluble. What I mean by what I said just now is that you're taking two different clear solutions, and when you mix the two, a solid precipitate gets generated. An ideal example for this would be the generation of lead 2 iodide when you combine lead nitrate, lead 2 nitrate, that's what I should say, being a nitrate that's going to be completely soluble, and you mix it with potassium iodide, being a potassium salt that will be completely soluble. And when you mix the two, you switch the ionic partners, you're going to end up with lead 2 iodide, PbI2, plus 2KNO3. Potassium nitrate is going to be completely soluble, and PbI2 is your solid. So realize this is a precipitation reaction. However, the terms whether something is soluble or insoluble are sort of the extremes in a continuous range of solubilities. Like we discussed in this particular chapter, we are going to take a look at the degree of solubility. So many compounds which are otherwise considered insoluble could actually be slightly soluble, or even those they might have a limited degree of solubility or a very small solubility product constant. So looking at the KSP values, we will hopefully have a better understanding for precipitation reactions from what we discussed in chapter 4 to now what we know of as equilibrium. So this can be done by revisiting what you learned in chapter 14, and that was the reaction quotient Q. Recall that the reaction quotient for any reaction was essentially setting up the equilibrium, but at a time other than when the equilibrium has been reached. So the reaction quotient for the reaction by which an ionic compound dissolves is the product of the concentrations of the ionic components raised to their stoichiometric coefficient. What that means is that if you had CaF2 in equilibrium with Ca2 plus and 2F minus, the ionic product, so sometimes you can write it as IP, some people continue to use a Q for the reaction quotient, is going to be equal to Ca2 plus times F negative and square of that. Realize that this is going to be exactly the same way as a KSP is written, because a KSP is the equilibrium constant and Q is or IP, the ion product, is the reaction quotient. And so depending on the value of the reaction quotient with respect to KSP, we would be able to predict whether we have a supersaturated solution and precipitation should occur, whether we are at equilibrium, or whether we have an unsaturated system. So if you have a solution where the ion product is less than the KSP, that would mean the precipitation will not take place and you will have an unsaturated system, and the equilibrium will proceed towards the right. That means it will proceed towards the products. Consequently, if the solution contains any solid CaF2, that CaF2 would eventually continue to dissolve. However, if all the solid has already dissolved, then the solution is simply going to remain as is, and it's going to contain less than the equilibrium amount of the dissolved ions. That's what it means. And like I said, such a solution will be called as an unsaturated solution. The precipitation is not going to take place. If you add more solid to an unsaturated solution, it will dissolve as long as the ionic product remains less than the KSP. Now, If you consider a situation where the ion product is going to be equal to KSP, what happens then? In this case, the reaction is at equilibrium. So we have set, we have achieved the equilibrium. It's a saturated system. No more of the solid can be dissolved. So we cannot make progress in either direction. Such a solution will most likely contain at least a small amount of solid in equilibrium with its component ions. However, the amount of solid may be too small to be visible, and like I said, it's going to be called as a saturated solution. And now if you have a situation where your ion product is greater than KSP, in such a situation, the reaction is going to be considered supersaturated, and the reaction is going to proceed in the backward direction. That means towards the reactants. That means solid CaF2 will be generated in the system because you have too much of the ions in there. So in other words, the solid normally precipitates out of a solution where the reaction quotient is greater than KSP. So this condition, if that is met, precipitation will take place. If it's less than KSP, precipitation does not occur, and when it is equal to KSP, we have a saturated solution. So a lot of times you might need a small seed crystal of for a reaction to start precipitating, and by doing that you're essentially bringing your solubility, you're forcing the backward reaction to take place. So again, one more time, just to summarize, reaction quotient greater than KSP, precipitation takes place. Reaction quotient less than KSP, no precipitation occurs. Equal to KSP, that's your saturated solution. All right, now hopefully you can see that because of this relationship, you would be able to essentially predict whether precipitation will occur or not when you mix two solutions containing dissolved ionic compounds. You can figure out the Q for the product, and hence you would be able to determine whether or not precipitation is going to be possible. So let's take a look at this question. The question is, will a precipitate form on mixing equal volumes of the following solutions? You have 3 times 10 to the power of minus 3 molar BaCl2. You have 2 times 10 to the power of negative 3 molar sodium carbonate, and they have given you the KSP as 2.6 times 10 to the power of negative 9 for the barium carbonate. So let's write down the reaction first. You have BaCl2, which is reacting with Na2CO3. Your product for the precipitation reaction is NaCl, and BaCO3, which is the solid. So the equilibrium that we have to talk about is BaCO3, which is an equilibrium with barium ions and carbonate ions. So hopefully you can envision that just the way we would have written the KSP, the reaction quotient or ion product is going to be the product of the concentration of barium times the carbonate. Now, a couple things here. They have the way they have worded the question. The question is, will a precipitate form upon mixing equal volumes of the following solutions? So the concentrations of BaCl2, which is given, is a stock solution. You're going to take maybe 1 milliliter of that. So realize that the number of moles that you would be talking about is not going to be, all of the 3 times 10 to the negative 3. But we are mixing equal volumes. So what that means is if you began with, let's say, a liter of BaCl2 and a liter of sodium carbonate, then since it's equal volumes, essentially the molar concentration will just be divided by 2. So the concentration of barium is going to be 3 times 10 to the power of negative 3. Divide that by 2. The concentration of carbonate is going to be 2 times 10 to the power of negative 3. You also divide that by 2 because the volume is going to get doubled up. And so when you try to solve this, this is going to be 1.5 times 10 to the negative 3 times 1 times 10 to the negative 3, or 1.5 times 10 to the negative 6 is the number. And the KSP is 2.6 times 10 to the negative 9. So the value that you have gotten is like way higher as compared to like 1,000 folds more than the value for the KSP. So since the reaction quotient is more than KSP, we would say that precipitation will take place, will occur. Your dry lab has good practice for this as well. Let's take a look at another one, which is along the same lines. So we have barium nitrate this time and sodium carbonate. So let me erase, make room for what we want to discuss next. So we have barium nitrate, and I'm mixing that with sodium carbonate. So barium NO3, which is aqueous, is being mixed with Na2CO3, and again barium carbonate is going to get generated, plus 2NaNO3. So we have essentially the same concept. We have the same equilibrium to worry about. I'm going to determine the IP. It's equal volumes that we are taking. So barium is coming solely from the barium nitrate. So I'm going to use that concentration, 1 times 10 to the negative 5th divided by 2. And I'm going to use 4 times 10 to the negative 5. Divide that by 2 as well. So your value looks like is going to come out to be 1 times 10 to the negative 10. And that value is less than, this is less than the 2.6 times 10 to the negative 9, which means precipitation is not going to take place, won't occur. So we saw two different cases. Again, please realize on the wording of the question here is asking, they did not give us, and we had to assume. We started with assumption that, okay, we mixed maybe a liter. And if you wanted, you can do a milliliter, the whole idea is that the concentration is going to be half of what you begin with. Sometimes there might be questions in which they will word the question in a sense that they will give you, and I'm going to solve one of those as well, that upon mixing, the net concentration is 0.01 molar with respect to BaCl2, and it's maybe 0.015 with respect to sodium carbonate. So they're saying after the mixing has occurred, what the final concentration is. So there's a subtle difference between the two things that I want you to be aware of. Right. Let's take a look. And this is exactly actually what I was referring to. The question is, from each of the following ion concentrations in a solution. So they're saying that after the mixing was done, the ion concentrations were found to be these. Predict whether a precipitate will form or not. So hopefully you can see that in case of barium and fluoride, if you had to determine the ion product, you would be looking at the concentration of barium, concentration of fluoride, and just basically multiply the two numbers, 0.015, and see what that value would be, and then compare it to what? Compare it to value of barium fluoride in the table. So in your test, that entire table of all the values that you will be needing will be provided to you, and then it's up to you what you wanna pick up. It's actually 2.45. Okay, so here I have 2 times 10 to the negative 2. Here I have 1.5 times 10 to the negative 2. And so I have 3 times 10 to the negative 4, which is higher than 2.45 times 10 to the negative 5. So yes, precipitation occurs. If you take a look at the second one, let's do that in blue. We have PbCl2, so that's lead, Pb2 plus. Chlorine is 0. Cl negative is 0.15, so 0.035 times 0.15 square of that, and that's going to give you the value. KSP for PbCl2 is 1.17 times 10 to the negative fifth. And so when you punch in these numbers, you get 7.87 times 10 to the negative 4, which is higher than the KSP value. So again, the precipitation will occur in this case as well. Let's take a look at another question. The question is, the following solutions are mixed: a liter of 0.00010 molar sodium hydroxide, a liter of 0.0020 molar magnesium sulfate. And so hopefully you can see that the products are going to be MgOH whole twice plus Na2SO4, and is a precipitate expected. So what would you see? Hopefully you can see sodium salt, of course, is going to be AQ, that's soluble. It's MgOH whole twice, which is going to be in equilibrium with magnesium and hydroxide. So if you have to write down the IP, you would say it's the product of magnesium times the hydroxide, and we are going to take a square of that. Now, magnesium, the concentration is 2 times 10 to the power of minus 3. Hydroxide, the concentration is 1 times 10 to the negative 4 square of that. And so your overall value is going to be 2 times 10 to the power of negative 11. And I'm going to compare that value again to the magnesium hydroxide value that we know from the solubility table. So magnesium hydroxide, the solubility is 2.06 times 10 to the negative 13. Since this is 100 times greater, we would say yes, the precipitation will take place. All right, I will discuss another question which is not actually in your PowerPoint, but I still want to kind of give you a feel for that, in terms of numbers. The question is, a solution containing lead nitrate. So a solution containing lead nitrate, lead 2 nitrate rather, is mixed with, what am I adding to it? Sodium bromide, NaBr, to form a solution, that is 0.015 molar with respect to lead nitrate and 0.0035 molar with respect to sodium bromide. Will a precipitate form? Will a PPT form? Realize the wording of this question. In this case, they're telling you that after the mixing occurred in your net solution, it was 0.015 with respect to lead nitrate and 0.0035 with respect to sodium bromide. And the whole point of doing that is essentially to give you the concentrations of the lead and the bromine. And so hopefully you can see that when you're mixing PbNO3 with NaBr, you'll need 2 of these. You're going to end up with 2 NaNO3 plus PbR2. So that's going to be your solid. So your equilibrium in question is Pb2 plus 2Br negative and aqueous and aqueous. And so the ionic product is going to be Pb2 plus Br negative, and it's going to be a square of that. So the lead is going to be 0.015 The Br minus is going to be 0.0035 square of that. And when you plug those numbers in, you're going to get 1.8 times 10 to the negative 7. And this number that you have, if I compare that to the KSP value from the table, and I'm looking at the table right now, lead bromide is at 4.67 times 10 to the negative 6. This table is in your book. Again, that value will be provided to you. But if it is a question from, in a dry lab or something, then you better have that table in front of you so that you're able to solve those questions. So here, notice the value that you got, that's less than the value for the KSP, and that would mean that the precipitation will not take place. So precipitation won't occur in this case. Now, there is a concept of selective precipitation, which is a process in which a solution that contains different dissolved metal cations, those cations can be separated from each other by a process called as selective precipitation, in which what we do is we add a reagent which forms a precipitate only with one of the dissolved cations. Just to give you an example, let's say you have seawater. Now, seawater we know contains magnesium as well as calcium. Both of those are present, okay? And those are present, usually concentrations are like 0.059 molar for magnesium, and calcium is a little bit less, 0.011 molar for the case of calcium. If you wanted to separate these by adding a reagent that will precipitate one of the ions but not the other, then you will need to take a look at the various different salts for both of these. So for instance, notice in your table, magnesium hydroxide is the KSP of that is like really low. It's 2.06 times 10 to the power of minus 13. And for calcium hydroxide, it is partially soluble, so 4.68 times 10 to the power of negative 6. What that means is that if you add hydroxide, it's going to form precipitate with the magnesium much faster because it is and at a lower concentration than it is going to do with calcium. That means that soluble hydroxides such as potassium hydroxide or sodium hydroxide, it will be a great precipitating agent because when you add the appropriate amount of the NaOH or KOH to the seawater, it's going to cause precipitation of the lesser soluble magnesium hydroxide but not calcium hydroxide. Of course, you will have to do, the math ahead of time to kind of figure out how much of the sodium hydroxide you will need, but that can be done. And so you would be able to separate out and measure the amount of magnesium that was present in that sample of seawater. So a lot of times properties such as, KSP can be utilized to separate out components, to determine, to study, the nature and behavior of materials around us. And so just to kind of, give you a flavor for how to go about that, I want to, kind of just give you an idea how to determine what is the minimum amount of hydroxide that you will have to add, which will trigger the precipitation of magnesium in a sample of seawater. So realize that the precipitation will commence when the value of the reaction quotient for the precipitating compound is equal to KSP. So when the IP becomes equal to KSP, that is when we say precipitation begins, right? Any value greater than that, precipitation is going to occur left, right, and center. But it begins. So the answer to what is the minimum that lies, that we have to look for that equilibrium. So your reaction quotient really is essentially magnesium times hydroxide, and we're going to take a square of that. And because the reaction quotient is supposed to be equal to Ksp, I might as well use that value directly. And so since magnesium, I talked about that, the concentration is 0.059 and hydroxide is the square. I'm just going to solve for the hydroxide and that will give me my answer. So dividing both sides of the equation, Bs is for both sides, by 0.059 and taking a square root. And take square root. And the hydroxide comes out to be, let's see, 2.06 upon complete solution. This is what I'm getting, 1.9 times 10 to the negative 6 molar. And that'll be your answer. So if you are able to generate a net concentration of the hydroxide, which is 1.9 times 10 to the negative 6 in the solution, you would be able to trigger the magnesium hydroxide precipitation. All right, now there are a lot of factors that affect the solubility. Of course, temperature is one of them, but not just the temperature, which will basically create space for the solute. A lot of times, depending on the nature of other ions that are present in the system, that too can affect the solubility. So just to give you a flavor, magnesium fluoride in pure water is going to give you an equilibrium that looks like Mg2 plus plus 2 fluoride ions. Now, if we try to create the solution in a solution that already contains sodium fluoride. So let's say I have some sodium fluoride already in the mix, and since sodium fluoride is going to completely dissolve and give you 100% Na plus and F negative, that means you have just pumped in fluoride ions in the system. Due to the common ion effect, hopefully you can see that the equilibrium will move in a direction to undo that effect. What that means is that the fluoride will get used up, the backward reaction will be triggered off, and magnesium is going to use up that fluoride and precipitate off more and more MgF2. So it will make the MgF2 less soluble. You can perhaps envision this on the basis of what you know from lab 16. So in that lab you had recall the silver chemistry. We had like silver nitrate, so AgNO3, which gives you lots of Ag plus and NO3. It's completely soluble. And then to that we added HCl, right? So that precipitates off AgCl. Now that AgCl, which is a solid, it's an insoluble solid, is going to be in equilibrium with the silver ion and the chloride ion. And if you add ammonia to that, essentially that ammonia reacts with silver to form a new complex, which is called as silver diamine complex. So this is written as AgNH3 twice with a positive charge. And so because you're removing the silver from the system, so you're removing this, what does that tell you? That tells you that more and more AgCl is going to dissociate to give you more and more silver and chloride. What that tells you is that upon the addition of ammonia, you are going to dissolve that precipitate of AgCl. So recall the equations that you had. AgCl which was in equilibrium with Ag plus and Cl minus. And now this Ag started to react with ammonia to give AgNH3 whole twice with a positive charge. Now, and I'm going to talk about the complex ions in a second, but realize what is happening is we are removing the silver from the equilibrium, the first equilibrium. So more and more AgCl is going to dissociate and give you the aqueous silver and chloride. And so we can say that addition of ammonia leads to dissolution of AgCl. Now, what would happen if you add some kind of a acid? How about you pump in HNO3, nitric acid, okay? Or you can pump in HCl if you want to. If you pump in HNO3, essentially you're going to remove ammonia as ammonium. So you're going to free up the Ag plus, or you would say that the backward reaction is going to take place. That means now you're going to start pumping in and reforming Ag plus in this first equilibrium. And what that means is that more and more AgCl will reprecipitate. So you can remove or make it reappear, make the AgCl reappear. You can make it dissolve, or you can regenerate it by addition of a weak base such as ammonia, which is able to complex with silver, or change the pH by having the H plus react with ammonia so that you can free up the silver ions, and then it will be available to interact with the Cl negative and regenerate the AgCl back into the system. So really it depends on what you have in your equilibrium and how quickly you have been able to remove that, to see how the Le Chatelier principle is going to move the equilibrium towards which direction.